Yeah. Okay, so inductive reasoning or simply induction is a way to decide if something is true or false. Conclusions. It's what inductive reasoning is based off of. Okay, so you gain a conclusion from your inductive reasoning. You do this in science class a lot, yes?
Yeah.
Okay, so these should be familiar terms for you. We're going to apply them to math. So you're going to start in geometry. You know how like in algebra, you would solve an equation that says 3x plus 5 equals 12, and you'd solve for x by subtracting 5, dividing by 3. Okay, we're going to do the same kind of concept, except for we're going to tell why that's possible when we do it. So we can do this because this rule tells us this. We can do this next step because this rule tells us this. So you're backing up everything you're doing, okay? You're backing up everything to prove that you are correct. So we're going to gain conclusions in geometry class by using inductive reasoning. Okay. Okay. Can I switch slides?
Yes.
Okay. So, with inductive reasoning, we are then going to do some pattern things with it. We can do patterns with shapes. We can do patterns with numbers. You guys have done this before. You just didn't realize it was inductive reasoning. Okay? So finding patterns. Finding the next number in each pattern or each sequence. We're going to have to start doing that type of stuff. If I go 3, 4, 6, 9, 13. What do I know about 3 and 4? It is separated by 1. What is 4 and 6 separated by?
2.
What about 6 and 9? Is there a pattern?
Like going up.
It's going up by 1. So what would be the next number if this is separated by 5?
18.
18. Okay? You used inductive reasoning to figure that out. And you came up with a conclusion. Okay? Inductive reasoning, conclusion. Here's the next one. You go 0 to 1. You go 1 to 4. 4 to 9, and 9 to 16. What does our pattern appear to be here? 0 to 1 is a difference of 1. 1 to 4 is a difference of 3. 4 to 5 is a difference of, go Elle, what do you think?
By threes?
By,
Thirds?
not thirds.
Odd numbers? 1, 3, 5.
Yeah, like
I mean,
odd numbers, yes.
7.
1, 3, 5, 7, and then this one would be 9, so it's 16 plus 9?
27. No, 25.
25, okay? So you found a pattern by using inductive reasoning, you came to a conclusion, okay? So you're gonna have to show me those patterns like I just did there, okay? So that's what I want to see work-wise so that I can tell how your mind's thinking. Okay, those are simple ones. We're going to get into more complicated ones in a little while. Can we handle the simple right now? Yes. This is what we're doing. There's a little bit more too. We're going to look at pictures too.
Yeah. You like pictures?
Okay.
I'm so sorry.
Okay. What is the pattern in the difference between the squares of numbers? Okay, think about that sentence. What is the pattern in the difference, which means I'm doing subtraction, between the squares of numbers? So, what is the square of 1?
1.
Okay, so 1 squared is 1. What is the square of 2?
4.
4. What is the square of 3?
9.
What is the square of 4?
16.
What about 5?
24.
Okay, so think about this pattern. I gave you some to look at, okay? They want to know, what is the pattern in the difference between the squares of those numbers? What pattern is happening here between the difference of the squares? Okay, what?
Is it the same as the last one?
Is it the same as the last one? I don't know. Let's see.
No, it's multiplied by
This is a difference of what?
3.
3. This is a difference of,
5.
this is a difference of,
7 again.
this is a difference of.
9.
So the last pattern we discovered was actually the difference between the squares of numbers. Okay? We just changed the wording and It's still the same conclusion and the same
So
pattern.
we would say it's going up another.
Yes, so what would be the next number in this sequence then?
36. Going up.
What?
36.
36, because I would add 11 to 25, right? 36. That way when we get into large numbers and I want to know what is the 19th number in this sequence, you could just apply the rule to it and it would be much easier. Does that make sense? Okay? Than trying to do the math all the way. Okay. A fractal, okay, is a pattern that is repeated at every scale. So we did scale factors, okay? There is something called a fractal, and it's a pattern that is repeated at every scale. So that if you zoom in, you are seeing the same pattern you would see at a distance, okay? So like in biology, sometimes, right, you see like an object you're studying, it will have a pattern to it, like a snake skin, okay? When I zoom in on the snake skin and put it under a microscope, that snake pattern still has the same pattern going on even at a smaller scale level. That's what this is talking about, okay? Does that make sense? So your scale factor basically is the same pattern as your larger object or your smaller object, okay? So a fractal is a pattern that is repeated at every scale, so that if you zoom in, you're seeing the same pattern you would see at a distance. Okay. A conjuncture. I love conjunctures, and I don't know why. They're just like my favorite thing in this part of math. Conjuncture. Okay. A conclusion reached by inductive reasoning. It remains to be proven true. So it's not a true statement. You have to prove that it's true. You could prove that it's false. It remains to be proven true. So when something says this is a conjuncture, it's a conclusion you've reached by inductive reasoning, but it doesn't mean it's true yet. In science, that happens a lot, right? You come up with conclusions after studying small little patterns in how you raised something or how you grew something. But that doesn't mean across the world that that's true statement, because you need to then take it to a larger scale and study it again. Does that make sense? What I'm saying? Okay, so a conjuncture is a conclusion reached by inductive reasoning. It remains to be true, proven true. Then you have something called a counterexample, and it's exactly what it says. It's an example that proves a conjuncture is false. It counters it. Okay? So a counterexample is an example that proves a conjuncture is false, which we're going to come up with a bunch of these on our own too. We're going to practice them. And in the Bible, there's a bunch of these when you're reading through it, and in things that you do every day, there's a bunch of these things that can be proven. So we're going to actually do a little activity tomorrow with this, just for fun, to think outside of the math realm into the real world. No, you'll have homework tomorrow. Okay, can I switch that slide? How are we doing with copying it down? Good. Good. Okay. Oh, that is the end actually of this lesson. But we're going to look at one other example in picture 4. Okay, so if you have this, let's say I have a triangle, okay? And we're going to say that this whole triangle is colored in, okay? And then I have a triangle, and these portions are colored in. And then I have a triangle. Oh, this one's going to be harder. I'm going to struggle with this one. Hold on. And boom. Let's divide it into 2. Oh, I like it. That's divided into 2. And then I'm going to go here. And then I'm going to go. Okay, and let's see what's colored. This is colored. This is colored. that big one blank. This is colored. This one's colored. And these two. Okay. They wanna know what would be the next pattern in this. Oof, right.
The whole thing would be black.
Three more triangles, what do you mean
Oh,
by
that
three
whole
more
thing's
triangles? Three more little ones? Okay.
Oh, there's little
I'm gonna make this one bigger so that I can actually fit them in here, that's why I'm doing it. Okay.
There's 5 like 5.
So, it is gonna be extra big because it takes a lot, I'm not a good artist either. Okay, so I do have one big one still here. Okay. And Doug said I have three little ones, which he's correct about, I just have to figure out how to draw that. So I scribble. There's one. Okay, and then there's a big one here. And then these should be split into little, I just can't draw it that well, I'm sorry, I'm trying. Okay, and then these should be split into, I think my book touched the board. Into little ones there. And then you have a big one again, right? Not like that. I have a big one that's gonna touch.
Oh.
I know. You can hate me.
Your board is annoying.
I know, I'm sorry. I need to get it fixed and I just have it because crap, I messed everything up. I know, shut up. Oh, I know what I did. This needs to be like, I don't know what I did. This needs to be here, right? That needs to come here, this needs to make a point. Okay, pretend that's pointy and we'll pretend it's perfect. And then it goes like, and then it goes, let's fix this other side. From here, it goes, it's on page 121. And from here, it goes and breaks down into different ones. Oh, I should have flipped it, that's why. Can't visualize this. I'm not a good drawer. And then it has a big one. And then it has little fellows on the outside. What is like this? You have a big one. Boom. So that's what that side should look like. So anyhow, it's gonna increase by 3 every time, okay? So you might have to look at some patterns of pictures too and pick out what comes next, okay? That's what we're looking at in your homework. It's mainly pattern stuff. The first 6 are all multiple choice, and then after that, it's like, here's a list of numbers, tell me the next one in the sequence. Here's a picture, tell me the next one in the sequence. Okay? It's 23 total problems. You've got this, let's go.
I'm so tired.